Okay, section 2.6, number 15. It helps to read the directions, everybody, which I didn't do at first. We're supposed to evaluate this using the squeeze theorem. This is kind of an interesting problem, and it didn't jump out at me as a squeeze theorem problem right away because of the double cosine. But now that we know that, all right, let's take a look at what we can do. So step number one to using the squeeze theorem is to isolate the trigonometric portion of the original function. And what I think we're going to focus on is this part right here, which can be a little bit scary, but it's cosine of some angle. And it doesn't really matter what that angle is, although in this case, the angle we're taking the cosine of is the tangent of theta. But it doesn't matter. Cosine of anything is always limited to a value between -1 and +1. So this is what step number one would look like. We've made this trigonometric portion of the function bounded. So now we move on to step number two, and that is to algebraically manipulate all three parts of this blue statement to make the middle part right here look like this. So what's missing? It needs to get multiplied by cosine of theta. So we're going to do that on all three parts, the left and the middle and the right over here as well. So here we go. Our left side now becomes the opposite of cosine of theta, needs to be less than or equal to, and the middle part is now cosine of theta multiplied by the cosine of the tangent of theta, which has to be less than or equal to just cosine of theta here on the right-hand side. So step number two is done. The middle portion, sorry about that, the middle portion here now looks like the actual function we're taking the limit of. And the only way this works, everybody, is if the lower limiting function right here and the upper limiting function right here have the same limit as theta approaches your value, your a value, which in this case is pi over 2. Well, lucky for us, cosine of pi over 2, your x-coordinate at pi over 2, which is right up here at 12 o'clock, is 0. So that value is 0, and the opposite of that is 0 as well. So now, I guess I'll go to step 3, and I just need to write out my answer. I'm going to say since, or because, that would be fine too, the limit as theta approaches pi over 2 of our lower limiting function, the opposite of cosine of theta, is equal to also the limit as theta approaches pi over 2 of your upper limiting function here, cosine of theta, and now's the time when we say what those limits are. They're both equal to 0. Then we can conclude now that the limit as theta approaches pi over 2 of this middle function right here, which is cosine of theta multiplied by the cosine of the tangent of theta, that limit has to equal the limit of the lower and upper limiting functions that squeeze this one here in the middle. Therefore, that limit is going to be 0 as well.